Now that we're familiar with composition, I want to explain how some functions are opposites of each other using composition. We are going to call opposite functions compositional inverses. Let's start with an analogy to explain what I mean by two functions being opposites. Two numbers can be opposites or inverses in a bunch of different ways. For instance, you might think of 3 and -3 as opposites, since if you take a number, add 3 to it, and then add -3, you get back to the number you started with. Instead of calling 3 and -3 opposites or inverses, we call them negatives of each other. You can check that they're negatives of each other by adding them and checking that you get 0. In a different way, you can also think of 3 and 1/3 as opposites of each other. If you take a number and multiply it by 3, and then take the result and multiply that by 1/3, you get back to the original number. We call 3 and 1/3 reciprocals. You can check that two numbers are reciprocals by checking that their product is 1. Now I'd like to define the compositional inverse of a function. If you start with a function which takes values in a set x to values in a set y, then its compositional inverse is another function, we'll call it g here, which maps from y back to x. It also needs to satisfy two more conditions. You need to check that f composed with g takes every element, little y and capital Y, back to itself, and you also need to check that g composed with f takes every element in x back to itself. Let's think about what this means. Since g composed with f of y is y, g takes an element y, produces a different element in the set x, and then f takes that element back to the set x, back to where it came from. F undoes what g does. The second condition, that g composed with f of x is x, tells us that g undoes what f does. I'll explain this in more detail on the next slide, but for now a few words of caution. Not all functions have inverses. If you start with some function f, you can't always find a function g which has the properties above. When you can find such a function, there's only one of them around, so we give it a special name, which is f to the -1. We say that's f inverse, or the compositional inverse of f. Although this notation looks like an exponent, it's not. The notation f to the -1, the notation f inverse, tells you how it composes with f. You should not confuse f to the -1 with 1 over f. The first is the compositional inverse of f, while the second is the reciprocal of f. Let's talk some more about how the inverse of f undoes what f does. We know from the definition of the compositional inverse that f inverse of f of x equals x. For example, f inverse of f of 2 is 2, and f inverse of f of 3 is 3. Let's suppose that f of 3 equals 1. What does this information tell us about f inverse? Well, f inverse of 1 is f inverse of f of 3, and for our rule for compositional inverses, that should be equal to 3. So, f inverse of 1 is 3. That is, the point 1, 3 is on the graph of f inverse. Similarly, if f of 2 is 0, then f inverse of 0 is f inverse of f of 2, which is 2. So if the point 2, 0 is on f, then 0, 2 is on f inverse. More generally, if f of x is equal to y, then f inverse of y is equal to x. This is how f inverse undoes what f does. It returns f's outputs back to its inputs. We also see how we can draw the graph for the inverse. If a point x, y is on f, then y, x is on f inverse. We just have to swap the coordinates. What this does is reflect the graph of f in the line y equals x, in order to get the picture for f inverse. Alright, now it's time to look at the formula for a function and its inverse. Problem 14 asks us to check that f of x equals 3x minus 2, and g of x equals 1/3 x plus 2/3 are compositional inverses of each other. There's two things to do here. We need to compose f with g and check that this function takes x to x, and we also need to compose g with f and check that it takes x to x. First, f composed with g of x is f of g of x, which is f of 1/3 times x plus 2/3. If we substitute 1/3 x plus 2/3 in place of x in the formula for f, we get 3 times, in brackets 1/3 x plus 2/3, minus 2. This equals x plus 2 minus 2, which is just x. So great, that's what we wanted. Now let's check the composition the other way around. If we compose g with f, then we get g of f of x, which is g of 3x minus 2. Putting this polynomial into the formula for g gives 1/3 times, in brackets, 3x minus 2 plus 2/3. This is equal to x minus 2/3 plus 2/3, or just x. So f and g are compositional inverses. Let's draw the picture for f and g. Since f is a line with slope 3 and y-intercept minus 2, here's the picture for f. G is a line with slope 1/3 and y-intercept 2/3. So you can check that g passes through the point 1, 1. So this is the picture for g. It's exactly the reflection of f in the line y equals x. In our last problem, we were asked to check the two functions were compositional inverses of each other. Now I'd like to start with a function and find its compositional inverse. The function we're given in problem 15 is f of x equals x squared, but on the restricted domain of all real numbers which are 0 and larger. We know that f of x equals x squared always outputs values that are 0 or larger, so we've given the range as the set of non-negative real numbers as well. Let's draw f of x on this domain. We omit the left half of the parabola because we are not considering negative inputs. If we reflect this graph in the line y equals x, we see what the graph of f inverse looks like. Let's see if we can solve for the equation for f inverse algebraically. We know that if f of x equals y, then f inverse of y is going to be equal to x. Here y equals f of x means that y is x squared. So to find the formula for f inverse, we simply have to solve for x as a function of y. So let's take the equation y equals x squared and take the square root of both sides. Thus the square root of y equals the square root of x squared. Since our inputs to f are either 0 or positive, we know that x is either 0 or positive, and thus the square root of x squared is just x again. If we rearrange this, we see that x equals the square root of y. So our formula for f inverse of y is square root of y. If you want to rewrite this with input x, you can. So f inverse of x is the square root of x. Our general process for finding the inverse of a function is to write y equals a function of x, and then to solve for x in terms of y. That function of y will be the inverse to our original function. You might be wondering why we restricted the domain in this problem. Let's look at problem 16. In this problem, we are asked to show that f of x equals x squared does not have an inverse if we consider all real numbers as its inputs. On this domain, we can easily draw the parabola given by f. If we reflect its graph in the line y equals x, we get this sideways parabola. This new graph, however, does not correspond to a function. If we look at the input x equals 4, then we can't determine whether f inverse of 4 should equal 2 or minus 2. This problem comes about since f of 2 is equal to 4, and f of minus 2 is equal to 4, and hence f inverse should be both 2 and minus 2. If you tried to solve for f inverse algebraically, you'd start with y equals x squared, and solving for x gives x equals plus or minus the square root of y, and that's not a function of y. I have one last problem for you on compositional inverses. Problem 17 asks us to find the inverse of f of x equals 1/4 x minus 3. Let's follow that process from before. We know that if y equals f of x, then x equals f inverse of y. So to find f inverse of y, we have to take y equals 1/4 x minus 3 and solve for x. If we move 3 over first, we get y plus 3 equals 1/4 of x. Next, I'll multiply by 4 to give 4 times y plus 3 equals x, or x equals 4y plus 12. So this is f inverse. F inverse of y is 4y plus 12. We can also rewrite this in terms of x. So f inverse of x is 4 times x plus 12. If we plot the line for f and for f inverse, you'll see that they are reflections of each other in the line y equals x. In a later topic, we'll talk about logarithms, and we'll see how compositional inverses are useful for solving equations.